So it's a strange question. Is quantum annealing equivalent to simulated annealing? Well, it cannot be. Classical mechanics cannot be equivalent to quantum mechanics, many of you may think. No. But some of you may wonder, well, it may be yes, because this is the second talk of a serious conference. So anyway, many of you may feel puzzled. So let's quantize it. It can be yes and no simultaneously. And this is indeed the message that I want to convey to you today. It is yes in some sense, but it can be no in some sense. So my slides are filled with equations, no pictures. So be prepared. I will speak as slowly as possible to the limit that you don't fall asleep. So let's define the problem. The first section is an overview. So this is a classical to quantum correspondence in the same spatial dimension. The target Hamiltonian to be minimized is denoted by H naught of sigma, where sigma is a set of Ising spins from sigma 1 to sigma n, each of which takes on values plus or minus 1. So this is the classical problem. And let's suppose that we run Monte Carlo simulations following the master equation, written here with a fixed temperature. We don't change the temperature as a function of time. So this is not simulated annealing in a strict sense. But let's suppose that we change the temperature very slowly, in quasi-equilibrium. And I also impose the condition of single spin flip. This is rather technical. I can remove this condition. But to be simple, I impose this condition for the moment. So the system follows this master equation. P sub sigma of t is the probability that the system is in the state sigma at a given time t. And W sub sigma, sigma prime is the transition probability that the next state is sigma, given that the present state is sigma prime. And I construct a quantum Hamiltonian out of this classical non-equilibrium dynamics at a fixed temperature by applying e to the 1/2 times beta, where beta is the inverse temperature, times h naught of sigma from the left, and e to the minus 1/2 beta h naught of sigma prime from the right, and minus sign in front of everything. And as you know, W sub sigma, sigma prime is not a symmetric Hamiltonian. The exchange of sigma and sigma prime generally change the value of this matrix element. But by this construction, I mean, by multiplying W from left by that quantity, from the right by that quantity, this quantity on the right-hand side turns out to be a symmetric quantity. So, and of course, this is a real matrix element. So this is a real symmetric matrix, Hermitian, so it can be interpreted as a quantum Hamiltonian. And it turns out this is a transverse field Ising model, because non-vanishing of diagonal element has sigma and sigma prime being different only at the single side, because this is a single spin flip process. So this is a transverse field Ising model. So this is a very simple way to construct quantum Hamiltonian out of classical dynamics. So this is a classical to quantum correspondence in the same spatial dimension. And it turns out this transformation from W to H gives the same energy spectrum for W and H. This transformation is called the similarity transformation, which doesn't change the energy spectrum, as I will show you later explicitly, up to the sign, minus sign over there. So if W has this spectrum, the largest eigenvalue of W is 0, which corresponds to the equilibrium state, because the equilibrium probability doesn't change with time. So the largest eigenvalue is 0 for W. And the next largest is minus lambda 1, minus lambda 2, and so on and so forth. And the Hamiltonian H, defined this way, turns out to have the spectrum starting from 0, the ground state, and the first excited state is lambda 1 positive, lambda 2 and lambda 3, and so forth. So these two Hamiltonians, these two matrices, share the same eigenvalue spectrum up to the sign.
Sorry, the beta is something?
Beta is the inverse temperature, which enters the...
So it means higher temperature,
Yes. Finite temperature classical stochastic process is mapped to the ground state of the quantum system. And if you look at this master equation, the largest eigenvalue is 0, which corresponds to the equilibrium state. And the next eigenvalue is minus lambda 1. And if you plug minus lambda 1 over here, you get this solution, of course, roughly speaking. So these are the two leading solutions, which means that the relaxation time towards equilibrium is the inverse of lambda 1 at a fixed temperature, non-equilibrium dynamics of classical Hamiltonian H naught of sigma. And of course, lambda 1 is the energy gap between the ground state 0 and the first excited state lambda 1 for the Hamiltonian, defined this way. So the energy gap of the Hamiltonian of the transverse Ising model corresponds to the inverse of the relaxation time of the classical stochastic processes. Therefore, if there is a phase transition in the classical system, then tau, the relaxation time, diverges very quickly at the first order phase transition, or by polynomial time, by polynomial power of the system size at second order phase transition for this quantity. It means that the energy gap of the transverse field, the corresponding transverse field, shrinks polynomially or exponentially. So not just the energy spectrum, but the rate of the closing of the gap are shared. So if there is a first order phase transition in the classical system, then there is also a first order phase transition in the quantum system. The same is true for the second order phase transitions. So in this sense, simulated annealing is equivalent to quantum annealing. I'm using the term quantum annealing in the same sense as adiabatic quantum computation for the moment. So this is the message. Classical to quantum correspondence. And the essential idea is indeed written in this paper almost 10 years ago by Castelnuovo and his colleagues. But I adopted their arguments such that it applies to the present situation of comparison between classical and quantum annealing processes. An example. Let's consider a very simple case of the one-dimensional ferromagnetic Ising model with a periodic boundary condition. And consider the classical stochastic Monte Carlo process of this simple one-dimensional Ising model and follow the prescription that I described. And I obtain this quantum Hamiltonian, the transverse field Ising model, by applying e to the something from the right and e to the minus something from the left. And this is the transverse field Ising model, but it has a strange term. I will explain the meaning, intuitive meaning of this term later on. So let's go on to some details of the mapping that I just described. This is the second section for classical to quantum correspondence. So it is about matrices and vectors of size 2 to the n or 2 to the n by 2 to the n. And for matrices, I use the notation with a hat above the symbol. H naught hat is a diagonal matrix with diagonal elements H sub sigma sigma, H naught sub sigma sigma, H naught of sigma. And W hat is a non-symmetric matrix. And P hat is a vector with a size 2 to the n. This is just the definition of the notation. And with these notations, the master equation is written like this in a very simple form. And since W is not a symmetric matrix, we should distinguish the right eigenvectors from the left eigenvectors. And I write the right eigenvector like this, psi hat super r comma n, with eigenvalue minus lambda n. And the largest eigenvalue is 0, corresponding to the equilibrium state, as I said before. It's written here. The equilibrium distribution doesn't change with time by definition, which is nothing but the Gibbs-Boltzmann distribution, of course, with inverse temperature beta. That is the partition function, of course. Then the general solution looks like this. It's a linear combination of all eigenvectors. The equilibrium state, psi hat super r, 0. And the next state is psi hat super r1 with the relaxation time lambda 1 inverse with the coefficient a1, which is determined by the initial condition, and so on, and so forth. So it is very clear that the relaxation time is the inverse of the first eigenvalue. Then let's quantize it. I'm just reiterating the same statement as I said before. By this definition of the Hamiltonian, H hat, it turns out this is a symmetric matrix, which is a consequence of the detailed balance condition of W. It's very straightforward to verify this statement. If we impose a detailed balance condition for this translation matrix, then this matrix, H hat, turns out to be symmetric. So it's real symmetric, so it's Hermitian. And it can be interpreted as a Hamiltonian of a quantum system. And the eigenvalues and eigenvectors are shared in some sense, in the sense that I will describe now. So W has the right eigenvector psi hat super Rn with eigenvalue minus lambda n, and H hat is defined this way. And if we define phi hat super n by this way, I mean that psi hat super Rn is multiplied from the left by e to the 1/2 beta times H hat, H0 hat. Then it is very straightforward to combine those three equations to yield this equation. It's a very short calculation, just 2 lines. So eigenvalues are shared, and eigenvectors are essentially the same. So in this sense, simulated annealing is equivalent to quantum annealing. And to be more explicit, let's write down the diagonal and off-diagonal elements of the resulting Hamiltonian. As I write here, the transition matrix, the non-symmetric property of the transition matrix W sub sigma sigma prime can be written like this, e to the minus 1/2 beta times H naught sigma minus H naught sigma prime. The non-symmetric properties of the transition matrix can be condensed in this form. And the remaining part, little w, sub sigma, sigma prime is symmetric. You can derive this relation from the detailed balance condition. So this matrix H sub sigma and sigma prime is written in this form by using this relation. So in this sense, H sub sigma, sigma prime is the matrix element of a symmetric matrix. This is the off-diagonal element, and diagonal element can be written very explicitly this form. So by combination of these two relations, the operator representation of the Hamiltonian looks like this, off-diagonal and diagonal. So it's very important that the diagonal element has this factor, H naught sigma prime minus H naught sigma, in which sigma and sigma prime are different just at a single site because we are considering single spin flip processes. Please remember this part. And assume that H naught is composed of the sum of local Hamiltonians, Hj's. By Hj, I mean the part of H naught which involves only sigma j. So the local field H naught, H0 sigma j, and two-body interacting part, which involves only sigma j and its neighbors, sigma k's. Here, the script n means the neighboring spins. J is here, and k's are over there on the square lattice, for instance. And other terms involving three-body interactions with sigma j. So this is the definition of sigma Hj. Then the quantity H naught sigma minus H naught sigma prime that appeared in the previous expression is very local because sigma and sigma prime are different only at site j. So all other sites cancel out. Only Hj remains. So the difference is just 2 times twice of the Hj. It's local. So this part can be written in a very simple way. So this means that the resulting quantum Hamiltonian involves only local interactions if the original H naught involves only local interactions. So local classical Hamiltonian is mapped to local quantum Hamiltonians. So this is the result that I showed before. And this terms is not familiar to us. It involves sigma z operators neighboring to sigma jx. Sigma jx is here, and sigma j plus 1 z is there, and sigma j minus 1 z is there. So this is the result of simple calculations, but let's try to interpret the inference, the meaning of this term intuitively. So this is the transverse field term that resulted from the mapping. And if we apply this operator to a state in which sigma zj minus 1 and sigma j minus 1 are parallel to each other, then this product is 1, which means the strength of the field, transverse field, looks like this, which is just 1, of course. But if we apply this operator to a state in which sigma j minus 1 and j plus 1 z are opposite, then it has this expression. And this is, of course, larger than that, which means that this unfavorable state gives a stronger field for the transverse field term. Whereas for this favorable state in the intermediate process of quantum annealing, it gives a weak field. So it's adaptive change of the strength of the field according to the present state. So this is my interpretation of this term. If you have any good idea, please tell me. So this is what I said already. As you know, if the transverse field doesn't depend upon such operators, then there is a quantum second-order phase transition in the one-dimensional transverse field Ising model. But if we, of course, we know that the one-dimensional simple Ising model at final temperatures doesn't have a phase transition. Correspondingly, this the transverse field Ising model with this term doesn't have a quantum phase transition. So this adaptive change of the strength of the transverse field can help us avoid phase transition in the quantum process. So it's homework. What happens to a very simple case of a single spin? So the answer is written here. So the deadline of submission is tomorrow. So the story so far has been for fixed temperature in simulated annealing. Then what happens if we change the temperature relatively quickly in the classical process? Can we map such a classical process to a quantum process? The answer is yes. Simulated annealing with inverse temperature as a function of time. We do the same. The difference only being that W matrix depends upon time through the time dependence of the inverse temperature. And we define H hat and phi hat in the similar manner, the difference being only in the time dependence of beta. Then it is very straightforward to rewrite this master equation in terms of phi hat by using these definitions. And the equation turns out to be like this. This is completely equivalent to that. And it looks a bit like a Schrödinger equation. But changing t to it, I is the imaginary unit, then it looks completely like a quantum Schrödinger equation with an additional term. So if we add this strange term, and if we change the time to along the imaginary axis, then these two systems are equivalent. This is the result that I obtained 3 days ago, so that I can catch up with this conference. So I don't have an example. It's a homework. The mapping so far has been from classical to quantum. Then what happens if we are given a quantum Hamiltonian and try to map it to the classical, corresponding classical one? There is a prescription, of course. And consider a quantum Hamiltonian with of diagonal elements, 0 or minus, stochastic as defined by the previous speaker. Of course, I have the transverse field Ising model in mind. But this, of course, excludes such a Hamiltonian, which is useful for some purposes, as we've described in a poster by one of my students, Yuya Seki. But forget about such a system for the moment. And the shift energy, such that the ground state has energy 0. This is a very simple process. And by the Perron-Frobenius theorem, the ground state of such a Hamiltonian has all elements positive, non-vanishing. Therefore, it is possible to take a logarithm of this element, phi sub sigma 0, and multiply by -2, which comes from this previous correspondence from the classical to quantum system. And this is a classical Ising model. But it has long-range interactions to accommodate various values of phi sub sigma. We should have such very complicated, in general, expressions of the classical Hamiltonian H nodes of sigma to accommodate various values of the elements of the ground state wave vector. So the classical to quantum correspondence was from local to local, but it is not the case the other way around. In this sense, these two processes are not equivalent. And transition matrix of the classical simulated annealing process can be defined as previously. So that ends the story. To summarize, equivalence holds in a broad sense. The eigenvalues of the transition matrix and the minus quantum Hamiltonian are the same. And the relaxation time, inverse of the relaxation time, is exactly equal to the energy gap of the corresponding quantum system. And this correspondence can be generalized to time-dependent cases, time-dependent temperature cases, from classical to quantum. But I don't know what happens from quantum to classical in time-dependent case. That's my homework. So the equivalence holds in a broad sense, but they are inequivalent in the sense that I just described. The classical to quantum correspondence gives local Hamiltonian from local Hamiltonian, but the other way around is not true. So in this sense, these two processes are not equivalent. Thank you for your attention.
I'm curious, can you try in that method of what we changed classical model? Did you look at the spectrum using Jordan-Williams transformation?
Jordan-Williams transformation. That Hamiltonian that you're saying that if I solve the strange-looking transverse field Ising model explicitly? No, it's not possible because it means to solve the classical non-equilibrium process is exactly. It's in general impossible.
No, I mean when you go to this, when you map classical to quantum, when you have circular terms like that, this one. Did you look at the spectrum?
No, no, not yet.
Because if you do Jordan-Williams, it becomes quadratic. Then this circular term goes away.
Oh, I'm not sure. Maybe. I am.
Then
But I don't think it can be solved exactly because it means to solve the one-dimensional non-equilibrium dynamics explicitly to the last detail. That's generally impossible. I don't believe so.
No, but the spectrum is
Really? Oh, well, I'm not sure. Okay, I'll consider. Thank you for your suggestion.